So this is the example of a reactor system in which two CSTRs are in series carrying out a first order reaction. So in the first reactor, 40% conversion is obtained. And the question is, how much bigger does the second reactor have to be so the overall conversion is 80%? And we're looking at our first order reaction. So we know the second reactor is going to be bigger. So if we're going to approach this problem, like most problems, it's really valuable to draw a representation of the process. It's a CSTR outlet, and we assume the second CSTR is larger. Liquid phase system. We have some flow rate coming in at a given concentration. So F sub A 0 is a molar flow rate coming in. 60% is on reactor. So if the conversion is 40%, 60% on reactor, it means the flow rate of A here is 0.6 of the inlet. We want overall the conversion to be 80%. So that means the flow rate here is 0.2. We'll call the volume of the first one volume 1 and volume 2. We're going to assume constant density. This is pretty reasonable since most CSTRs are going to be liquid phase systems. The rate of reaction, as we know it's a first order reaction, is like so. And so basically our question is not what the actual volumes are, because we don't have sense enough information. What is this ratio? So of course what we need to write down, mass balance for the system, steady state reactor system. And so we're going to run the reaction, then no accumulation in reactor. So if we look at the CSTR mass balance, accumulation for each component now is how much is flowing in, how much is flowing out, and then the other changes that result in accumulation is due to the reaction. So steady state means this is 0. The flow rate of A, remember we always are doing a balance on a given component, FA0, 6/10 FA0. So this is the first reactor, and then the rate of reaction in the reactor times the volume of reactor 1. So we now can substitute in based on our knowledge of the system. Of course, this difference is how much is reacted. The rate of reaction is first order reaction, rate constant. The concentration in the first reactor must be 6/10 of the initial concentration, because the exit concentration in the reactor has to be identical to the concentration in the reactor. So this is 6/10 Ca0, and that means this is 6/10 Ca0. Likewise, therefore, this is 2/10 Ca0 in the reactor, and this is 2/10 Ca0 leaving the reactor. So we can rearrange this equation, and the fact 4/10, so the flow rate coming in is a volumetric flow rate times the concentration coming in. So we can rearrange the equation. Ca0, of course, cancels out of the equation, and we relate K and volumetric flow rate. So we end up with 1.5 times K times volume of reactor 1 is equal to the volumetric flow rate. Or K is equal to the volumetric flow rate over 1.5 times the volume of reactor 1. So now we do the same type balance, steady state, but on reactor 2. Same ideas, difference being now the inlet into reactor 2 is not FA0, but it's the outlet from reactor 1. So that's the inlet. 80% conversion, it's the outlet. Rate constant, and now the concentration, as we mentioned, is 2/10 Ca0, and now it's the volume of reactor 2. So again, we can arrange, and let's just go ahead and make the substitution. The flow rate is the volumetric flow rate times the concentration. And this is 0.2 K Ca0 times V2. Again, the concentration Ca0 doesn't matter. So we end up with 0.2 rate constant. Volume reactor 2 is 0.4 times the volumetric flow rate, which means V2 is 2 times the volumetric flow rate over the rate constant. And up here we say that the volumetric flow rate over the rate constant up here, 2 times 1.5 times V1. So V2 is 3 times V1. So we get 40% conversion in the first reactor to get an additional 40% because the concentration is lower. And we could just look at the system and say in reactor 2, the concentration is only 1/3 of what it is in reactor 1, right? This is a 6, which means to get the same amount of reaction per time, the volume must be 3 times as large. So that this makes sense, and a simple check says this is consistent with what we would expect.